Okay, this is my presentation. This is the topic of my paper, Performance Analysis of Cloud with Queue-Dependent Virtual Machine. And this is outline. And first is introduction. One key feature of cloud computing is that resource can be accessed remotely via a web browser. Thanks to its scalability and easy maintenance, cloud usage has grown rapidly, making resource scheduling and performance management critical. When many applications run in the cloud, dynamical allocating resource based on demand improves performance and save energy. To achieve this system must support automatic scaling while meeting service level agreements. By practical performance based on system metrics and user experience, service quality can be ensured with over provision. And this is the model distribution. At first, on the far right, user sends a series of requests, such as R1, R2. These requests first go through a mission control, which determines whether to accept them based on the current system status, in order to prevent overload or resource shortage. And the second, once the requests are admitted into the system, the workload analyzer on the left analyzes historical workload information, and the load predict and the performance model predict the upcoming arrival rate and resource requirements. And third, the prediction resources are sent to the central application provisioner, which use them to decide whether to quit new virtual machine or release existing ones. It also feeds back the current system status to update the model parameters and improve the accuracy of future predictions. And fourth, after the application provisioner makes a decision, it instructs the resource provisioner in the lower layer to execute the operation of creating or destroying virtual machine. And this is the model and analysis system assumption. And this is the threshold policy. VN is always active, and when the number of requests greater than N1, VN2 is activated. When the number of requests drop below N, VN is deactive. Although the actual system deployment may involve multiple queues, the analyst simplifies the model to a single queue focused on performance analysis for dynamical VN activation. And this is the simulation program. My simulation is based on the two models proposed in the paper, Model 1 and Model 2. The main goal is to replicate and verify the theoretical analysis of VN utilization and the average number of customers in the system. I implement an event-driven simulation system in Python, which consists of three main modules. The first is the customer class, which replaces each customer is records their arrival time, service time, event, and the assigned VN ID. The second is sim event list, which generates a sequence of arrival events based on a given arrival rate lambda, using an exponential distribution. The third is queuing sim, a code simulation case which includes the logic for VN assignments, event handling, and the final calculation of performance metrics such as PB and L. And these results correspond to Model 1, where all virtual machines have identical service rate of 1. The left-hand figure shows the result from the original paper, while the right-hand figure presents my simulation outcome. As the arrival rate lambda increases, the VN utilization also increases. Since more incoming requests require processing, causing the VM to remain busy almost all the time. On the other end, when the number of active VM are increased, the authorization of each individual VM decreases, indicating that the workload is more even distribution across the VMs, preventing overload on a few machines. These figures show how the average number of customer errors increased with arrival rate lambda under Model 1. With fewer VM, the system becomes overloaded and error grows. More VM help reduce congestion and keep error lower. This section shows results for Model 2, where each VM has a different service rate. Similar to Model 1, VM authorization increased with the arrival rate lambda. Unlike Model 1, service rates grow with the VM index, making the system more efficient by reducing congestion and improving resource usage. And this figure shows the values of error under Model 2. The trend is similar to Model 1. As lambda increases, error also increases. But overall, the values of error in Model 2 are generally lower. These figures are based on Model 1, show how VM utilization changes with different system capabilities, okay, while keeping the number of VM fixed as R equals 5. As the arrival rate lambda increase, VM personalization EB also increase. A larger K allows the system to handle more requests, reducing jobs and increasing overall VM usage. And these two figures illustration change in the average number of customers in the system error under Model 1 as the arrival rate lambda increase. As lambda increase, the average number of customers error in the system also continues to rise. When K becomes larger, error also increases. This is because a larger K allows more customers to remain in the system synchronization, which reduces the probability of request jobs but also increases queuing depth, automatically leading to a higher overall error. These two figures show the result under Model 2, and we can observe a similar pattern to Model 1. As the arrival rate lambda increases, the authorization of each VM also increases. Compared to Model 1, the authorization values in Model 2 are generally lower. This is because the VM in Model 2 have heterogeneous service rate, where later added VMs have higher processing capabilities, leading to improved overall system efficiency. Under Model 2, the average number of customers in the system error is noticeably lower, and the growth of error is more gradual because the heterogeneous service rate helps distribute the load more effectively. And this is my conclusion. The paper addressed the problem of VM resource allocation in cloud system by proposing an analytical model based on queuing theory. The system is modeled as a final cavity multi-server queue where VM are dynamically activated or deactivated according to queue length using a threshold policy. And a Markov process is used to derive the steady state probabilities and computed performance metrics such as average system depth and VM utilization. The fourth, simulation results show that the proposed method effectively reduces waiting time and the resource waste, outperforming statistical resource allocation approach. This is my presentation. Thank you for listening.
So you have your own result and it shows the match or not match. For the figures seems to be the match result, but for the table some they don't have the perfect match result, right?
Yeah.
So about the part here, perhaps you need to reconsider how to have the beta accuracy. Yeah, I think you can reconsider. Of course, for the current one seems to be okay. Yeah, this one. I mean, with figures, the part of figures it seems to be okay, but for other results in tables, maybe you need to reconsider how to have the beta accuracy.
Yes.
Okay. Alright, so I think no problem for you. That's it. Thank you.
Okay, thank you.